All right, welcome back. So in a few minutes, we're going to continue our discussion of the pigeonhole principle. But first, let me tell you about one of my favorite mathematicians from history. His name is Paul Erdős. Erdős is an incredible person, very unusual. He loved math. He lived and breathed math. If you think I like math, you ain't seen nothing yet. I mean, this guy could spend 16, 18 hours a day doing math and do that day after day. And not because he needed to, it's because that's all he wanted to do. He wanted to research with others. Almost all of his research was done collaboratively. But that's what he wanted to do. And he was, in a time before worldwide travel, he was constantly moving around from country to country, continent to continent, visiting this math department over here and that mathematician over there, moving around and doing math with so many people across the world. It's kind of a beautiful thing, actually. His taste in math was just delightful. He loved, his tastes match my taste. I mean, the problems that he liked, he got into, were just so fun and interesting and subtle, and they're so often they have these beautiful creative solutions. I just loved his problems. And he carried so many problems around with him in his head. Easily hundreds, probably thousands, if not even more than that. Problems he could just instantly recall. And they could be solved problems that he just really liked the solution of, so he would show them to people. Or unsolved problems, open questions, which nobody knew the answer to yet. And he had this great sense of people, of mathematicians, their abilities, their interests. So he could find you the right, perfect problem for you. He's like, here's a problem that he thinks you're going to like, and it's going to match your skill set. So, no one knows the answer to this problem, but I think you are the ones that he believes can make progress on it. And so often he was right. He died in 1996 when I was 8 years old. So sadly, I never got to meet him, despite us having the same research field. And my PhD advisor was one of his closest collaborators. They published dozens of papers together. Erdős lived with my advisor, whose name is Ron Graham, and his wife Fan Chung, for weeks at a time, every year for many years. So they were very close. So I definitely would have had the opportunity if the timelines had matched up. Sadly, never got to meet him. But people who do meet him just speak so highly of the experience. I mentioned carries problems around in his head. Well, if he was meeting with some kids, some people who are their children or their teenagers maybe, but they're kids who have exhibited talent in math. Okay, so these are very strong students who aspire to be mathematicians. Students like that, Erdős would always be very, very happy and open to talk to them, to share problems with them, to encourage them in just a really warm way. So it's a very nice aspect to his personality, that he was always encouraging of the next generation. And Erdős, he would always have problems ready. So he'd meet a student and he says, hey, here's a problem. Why don't you work on this one? It could be a little research problem, or oftentimes it's just, hey, here's a problem. It's been solved. I know the solution, but why don't you try it out? And he'd have these great little fun problems for them. And his favorite problem to give them is this one. So here's the problem. He would ask them, imagine you have the integers between 1 and 200. So 1, 2, 3, 4, 5, all the way up to 200. You have those 200 integers. And I want you to prove that if you choose 101 of those numbers, no matter how you pick them, the 101 numbers that you choose must have the property that one of your numbers divides another one of your numbers. Does that make sense? So if you've chosen, do you know what divides mean, or is divisible by? So 15 is divisible by 3, right? Because 15 divided by 3 is 5. That's an integer. That's what it means to divides. 15 is not divisible by 10, because 15 divided by 10 is 1.5, right? It's not an integer. So he would give this problem to students. They're out at dinner. He's there with I don't know, a group of very strong students, and he's challenging them. He said, hey, why don't you think about this problem? Imagine you pick any 101 integers from 1 to 200. Prove that at least one of your chosen numbers will be divisible by another one of your chosen numbers. It's a good problem. Think about it on your own. I strongly encourage you to stop listening to me right now and pause the video and go off on a walk or sit down and take out some pen and paper and actually try it out. It's a good problem. And it's fun to try out different things because most likely your first guess is not going to work. And your second guess probably is not going to work, but you're going to learn something. You're going to get some insights from your first couple guesses. And by your fifth guess, you might have it. It does use the pigeonhole principle. And in the end, we want two numbers. One divides another one. So that suggests that we might be using the simple form of the pigeonhole principle because that one, the conclusion is that you get two of something. So that's a big hint. He oftentimes wouldn't give them the hint that use the pigeonhole principle. Oftentimes the students might not even know about the pigeonhole principle. But still, you can kind of logic it out without knowing it. So how would you do this? Hopefully you've gone off and you've thought about it a bit. What should your objects be? What should your boxes be? So the objects are, usually the objects are like, what are you given in the problem? You're going to be given 101 integers from this set. So those are probably going to be your objects. So if I'm writing out some scratch work, the 101 integers are the objects. I'll put the question mark. This is just scratch work. I don't know. At this point, we don't know the answer. But you can imagine, yeah, maybe these 101 integers are going to be our objects. So if we have 101 integers, we would need 100 boxes. So we need 100 boxes. If those are our integers, then we would be able to remove the question mark and say, yes, we would need 100 boxes. And what needs to be true about these boxes? We need to be the case that if two numbers are placed into the same box, then one divides the other one, right? That's the only way to ensure that if we do end up with two integers inside the same box, then we are definitely done, that we have found the two integers that we need, one being divisible by the other. So you can start imagining, okay, so we need 100 boxes where if A and B are in the same box, then A divides B, or vice versa, or B divides A. Okay, so that's what we're looking for. We need to say that if two numbers A and B end up in the same box, then one of those must divide the other one. That's our goal. So how could we do it? How could we create boxes to say, and we'd have to have some sort of rule to say, if you get 7, you have to know where does 7 go, which box does it go into. If you get 12, which box does 12 go into? So think about that. How would you set up boxes so that if two numbers end up in the same box, then one divides the other? You might think about divisibility. You might think about, I don't know. So 1 is good. 1 is a good number because 1 divides everything, right? So no matter which, if you ever choose 1, then you're good to go because 1's going to divide all of your other 100 numbers. But 1 can only end up in one of these boxes. So yeah, that might not be too helpful because it can only end up in one box. So, there's a good chance one of the other 100 boxes or 99 boxes is going to have the 2 numbers inside of it. So I don't know, if you have 2 in one of the boxes, what numbers should go in that box also? So you have a box that you have to say, okay, if you get 2, put them in this box, okay? So what other numbers should we put in that box? Well, 4, you could put 4 there. That way, if, 2 and 4, one divides the other one. Can you think of another number that also divides? So you could put 8 maybe. That makes some sense. So you could start listing off numbers and say, okay, I want 2, 4, 8. You could keep doubling 16, 32, 64, 128. Okay. So you could stick all of these guys into one box and say, if any of those numbers appear, maybe put them in this first box. Okay, well, this seems pretty effective so far. We just checked off 1, 2, 3, 4, 5, 6, 7 numbers. If one box covers 7 numbers, that's pretty efficient. So then what? You want to go to the next box and say, okay, should I just put 3 in it or something? And you have to be careful because, it'd be tempting to also put 6 in this box because 2 does divide 6, right? So suppose we said 2, 4, 6, 8, and you could say, oh, this is good. Put all the even numbers in the first box. But you have to be careful because if 2 is in there, so if within your 101 numbers, 2 and 6 are both chosen, then you're good. 2 does divide 6. But if within your 101 numbers, only 4 and 6 are chosen, then we don't have the case. It's not the case that one divides the other. So this is good because in this case, any one of these numbers does divide all the later numbers in the list. So that is good. So you could try to think of how I make other boxes have this property. So it's getting a little confusing, right? I mean, you could start thinking about prime factorizations. That could be one way to do it. Let's just brainstorm other ideas. Well, you have 100 boxes. So, you could think about the 100 numbers, maybe like the first 100 numbers. So you have a box for 1, a box for 2, a box for 3, etc., all the way up to a box for 100. Okay. And then you say like, well, inside of the, so all those numbers get put in a box. What about the numbers bigger than 100? Well, if all those numbers bigger than 100 had something less than that divides them, then you can say, okay, just pair them up. Like 3 could get paired up with 100 and 102. 3 and 102. You know that trick where if the digits add up to 3 or a multiple of 3, then the number is divisible by 3. Anyway, so you could say, oh, this is the box for 3 and 102. This is the box for 2 and 104. So if you ever pick 2 or 104, either of those two numbers, put it in this box. If you ever pick 3 or 102, put it in this box. And you could just try to pair them up. But that's not going to work, right? Because what about numbers like the prime numbers that are larger than 100? Those numbers don't have anything less than them that divides them, so they can't be put in a box. So, thinking of, okay, what are there 100 of? That's an approach, but it's not working out, do you see? So you could focus on the prime numbers. You could say, well, the prime number is bigger than 100. Those are the problems. Those are the only things that don't have something less than them that divides them. So maybe give them each a box. I actually looked it up. There are 20 of those numbers. So you have 80 boxes left. I don't know. Think about it. So what also there are 100 of between 1 and 200? You might notice that there are 100 even numbers and there are 100 odd numbers. So maybe you have one box for every even number? Or one box for every odd number? If you do one box for every even number, so you have 2, 4, 6, and so on. Okay. So you have to say, okay, where do the odd numbers go? Well, already you kind of get stuck, right? I mean, like, where should 5 go? Well, 5 could go into 10's box, I guess. So you could just double it. But then where does like 101 go? It'd have to go in the box 202, but there is no box 202, right? The numbers stop at 200. Okay, so new plan. What about the odd numbers? There are at least 100 of those. 1, 3, 5, and so on. Okay. So where should 4 go? Well, I guess we'll start with 2. So where should 2 go? I guess you could put 2 in the first box. So you could have 1, 2, 3's there, 4 goes there. 5, 6, where does 6 go? It can't go here because you have the same problem from before. What if 4 and 6 ended up in this box? Well, 1 doesn't divide the other. Well, oh, but 6 could go with 3, right? And then 8 could go here with 4. What about 10? 10 could go with 5. Do you see? So you could have one box that has like 5. And what else goes in this box with 5? How about you just keep doubling? You do the 1, 2, 4, 8, 16, 32, 64, 128, that thing. You just do it, but instead of starting at 1, you start at 5. 20, 40, 80, and 160. So maybe these numbers go into this box. And you say, you know, if within your 101 numbers, if you ever choose any of these numbers, put them in this box. And if you ever choose 7 or 14, you see I'm just doubling every time, 28, 56, or 112, then you put it in this box. Do you see? Then every number divides the lower number because each of these numbers has a 7 in it. If you think about prime factorizations, all these numbers have a 7 in it, and then just some amount of 2's. 7 or 7 times 2 or 7 times 2 times 2 or 7 times 2 times 2 times 2, you know, 7 times 2, 7 times 2 squared, 7 times 2 cubed, 7 times 2 to the 4th. Is this making sense? So basically, in general, you'd have box M, where M is an odd number. M is an odd number. Okay? And what numbers are going to be going into box M? Well, if among your 100 numbers, M is there, you put it in. Or, how do I write this out in the book? I think it's M times 2, or is it 2 times M? Not that it's that important. 2 times M. If you have 2M, you also put, if 2M comes up, you put that in box M. If 2 squared M comes up, you put it in box M. In general, any number of the form 2 to the k times M, you put that in box M. Do you see? This is tricky. This is a very subtle problem. But the idea is you have one box for every odd number. And every number, if you just take that number, if it's odd, you just put it in its box. If it's even, then just take away a power of 2. So divide by 2. Is it odd yet? No? Okay, divide by 2 again. Is it odd yet? As soon as you just keep dividing by 2 until it becomes odd, and once it's an odd number, that's the box it goes into. It's another way to think about it. So this should work, because if you have one number of this form and another number of this form, then you just divide them and you get a third number of this form, right? If you have 2 to the k, 2 to the k times m over 2 to the l times m. And you have the bigger number on top, so k is going to be bigger than l. Then what does this equal? Well, the m's cancel, and you just get a power of 2. 2 to the k minus l, right? Like if you take 28 divided by 7, you get 4, 2 squared. If you take 80 divided by 40, you get 2. 80 divided by 10, you get 8, 2 cubed. 160 divided by 5 is 32, right? I think. So 32, and 32 is 2 to the 5th. Okay, so that's how this works. Take some time to get there. It's more fun to discover it on your own. And if you discovered it on your own, you might have had a different way that you were thinking about it, and that's perfectly fine. But that's the idea. And let me pause this video briefly, and then I'll write up some sort of solution to this on the board right here using the pigeonhole principle. Okay, now let's talk about the proof. So I wrote up the formal proof on the board. So this, again, goes through using the strategy of one box for every odd number. So you have a box for 7. Okay, so what numbers, if you look at your list of 101 numbers, which numbers do you put into box 7? Well, if 7 appears in your list of 101 numbers, put that in box 7. Or if 14 appears, put it there, because that's 7 times 2. Basically, you just double it. If 28 appears, doubling it again, put that in box 7, etc. Okay? So, for each number n, from 1 to 200, factor out as many 2's as possible. So basically, if you start with any number, you start dividing by 2 until it gets to be odd. Eventually, you'll reach an odd number. Then write it as 2 to the k times m, where m is an odd number. Okay, so if you divide out a bunch of 2's, you get to some number m, and now you can throw the 2's back in to get back to your original number. So here's an example. It's okay to include little examples in your proofs, but an example in your proof is kind of like a picture in your proof. It's good if it adds clarity, but your proof should be logically sound without it. Okay, so if you suddenly remove this example, then your proof should still go through just fine without it. Okay, but here's an example of what we just did. So a number like 56 you could write as a bunch of 2's times 7, right? Because 56 is 2 cubed times 7. So if you keep dividing by 2, you get down to 7. 25 is already odd, so there's no 2's to divide out. So you could write that as 2 to the 0. There are 0 2's there, times 25. 25 is the odd number. Okay, so basically you're looking for the largest odd number inside of your number n, and then and everything else is just a bunch of 2's. Okay, so now what we do is we create a box for each odd number from 1 to 199. There are 100 such boxes. Place your 101 integers into these boxes based off this rule. Okay, so down here is the rule that you're saying to follow. If the integer is n, then place it inside box m if this condition holds, if n equals 2 to the k times m. So you look at your 101 integers, each one, that's your new n, write it like this, and whatever your odd number m is, put it in box m. Okay. So here's another example. 72 is, you could write that as 2 cubed times 9. So therefore, it would go into box 9. Okay. So since the 101 integers are placed into 100 boxes, this is where the pigeonhole principle kicks in. 101 integers into 100 boxes. Therefore, by the pigeonhole principle, this is the simple form of it, some box must have at least 2 integers placed into it. Okay, so this is good. We've did the big setup. We put our 101 integers into our boxes based off the rule. And now we're saying, okay, now we have a single box with at least 2 numbers in it. Okay, so what do those 2 numbers look like? We're hoping we can show that those 2 numbers have the property that one divides the other. Okay, so which box is it? We don't know, so let's just call it box M. Okay, so suppose it's box M that we have two numbers inside, at least two numbers. So pick the two numbers or two of the numbers inside that box. And suppose those numbers are n1 and n2. So write them as 2 to the k times m and 2 to the l times m. It's the same m in both cases because they're both in box m. And one of these numbers is going to be bigger than the other. Well, what determines whether they're bigger? It's all about this k and l. Whichever one of those two numbers is bigger is the bigger number. So one of them is bigger. Let's just assume it's the second one. So the first one's the smaller one, the second one's the bigger one. So this might be like 7 and 14, or 14 and 28, or 7 and 28, something like that. So let's assume the second one's bigger, meaning that this exponent L is bigger than that exponent K. Okay, now we just have to show that we did it correctly, that all the setup was done right, and that now we do indeed have one number dividing the other. So then we have found two integers where one divides the other. In particular, n1 divides n2, because if you do n2 divided by n1, that's this, the m's cancel, L's bigger than k, so this is just some other number, and that's an integer, so that completes the proof. Now in proofs, if you end with a calculation, or I don't know, just whenever it feels right, it's not uncommon to see statements like this completes the proof, just as like a final statement to signify, yes, the proof is now done. And don't forget your little box at the end, your Helmholtz tombstone, to signify that it's a visual marker that the proof is done. Okay, so there you go. It's a pretty interesting idea. We started with that first example where like, okay, well, what should we do with 2? Oh, let's add 4 and 8 and 16 and 32 and 64 and 128. And just thinking about the powers of 2, it's that exact same idea that's just generalized. So you could have 1, 2, 4, 8, 16, blah, blah, blah. You just keep doubling, and then as long as you just have powers of 2, then you're guaranteed that each pair of numbers in your list, the smaller one divides the bigger one. So it's that same idea. And it says, well, instead of having just the powers of 2, let's have the powers of 2, and then just multiply them all by 3, or multiply them all by 5, or by 7. And then it still holds. And just by doing that, you get all the numbers. So I think it's a pretty clever idea. And it seems to be inefficient, right? I mean, if you actually look at the boxes, like if you label out the boxes, so there's box 1 that has all the powers of 2, box 3, which has like 3, 6, 12, 24, etc. Box 5, box 7. Okay, they look like pretty good boxes. They have a lot of numbers that are being funneled into it. And then you look at the boxes for the odd numbers that are above 100, and they only have one number. Right? Think about box 101. What else goes into box 101? Nothing. Only 101 goes into box 101, right? So that's the only thing that goes into box 101. Box 103, box 105, 107. The 50 boxes, the last 50 boxes among our 100 boxes are guaranteed to never have two numbers be placed inside of them. It seems like that's kind of inefficient, right? You think you want to have it be all nice and balanced where, all the boxes kind of are paired up, two numbers in every single box. But no, that doesn't happen. Half the boxes it's impossible for those boxes to have two numbers end up inside of them. It's only the first 50 where it's even possible. And the first few get the lion's share, where you have, 1 and 3 and 5 and 7. Those boxes can be pretty full, and the other ones not so much. So, anyways, I think that's pretty interesting. And by the way, 100 is optimal. You can't beat 100, meaning if you pick you can't beat 101, meaning if you pick 100 numbers between 1 and 200, you're not guaranteed that one of them divides another one. You need 101 to have that be guaranteed. And given the inefficiency of the boxes, you might think, oh, we can probably do a lot better than 101, but you actually can't. 101 is the best you can do. So think about it. Give me 100 numbers from the set from 1 to 200, where one of them does not divide any other one. How about this? Go ahead and leave your answer in the comments. That's a fun little thing. Maybe I should do that more often. Leave your answer in the comments. So here's the question. find me 100 numbers between 1 and 200 where none of your 100 numbers divides any one of your other 100 numbers. And give me the answer in the comments. And what do you know? That's cool. That'll get some likes. Just gaming the system here. Okay, cool. So that is Erdős's favorite problem. He gave it to a lot of people over the years. If you happen to have a story about Erdős giving this problem to someone, to you or to someone you know, leave that in a comment too. Or you've seen it written down somewhere. That would be interesting too. I'd like to learn something. Or if you have an Erdős story yourself, leave that in the comments. There you go. Let's just leave a lot of comments. Let's talk to each other. That would be fun. Okay, so that is the end of the main content from chapter 1. So we've reached the end of section 1.3. So after that, there are other things. I have a section called bonus examples and some pro tips and things like that. So this video is getting long, so I'll make the next video, I'll talk briefly about what else, if you have a copy of the book, what else you can expect to see in the book. And then after that, we'll start chapter 2. All right, thank you for watching. See you next time.